Hi, and welcome to the course on Power Transmission Engineering. In today's lecture of Unit 1, Transmission Line Constants or Transmission Line Parameters, we are going to study about how to calculate the resistance of transmission line and what are the factors that are affecting the resistance and how do you calculate the resistance whenever the temperature of the conductor is changing. So we know that the all the conductors or all the transmission lines are made up of materials like copper or aluminum or ACSR. So we have seen in the extra desk class. So all these are metals and all metals have inherent property of resistance. Though this resistance is neglected when compared with the inductance in the transmission lines, but the effect of resistance has to be studied to understand the amount of copper losses or I square R losses that are dissipated in the conductor. Therefore, it is very important to study the effect of resistance to design an efficient transmission line. So let's move into the outcomes. After the completion of this lecture, you will be able to understand what is the resistance parameter of the transmission lines. You will be able to calculate what is the resistance of solid conductors. You will understand the factors affecting the resistance of transmission line. So transmission line parameters, there are four types of transmission line parameters. You can call it as series inductance, series resistance, shunt conductance and shunt capacitance. So here you can see in this diagram, here this is the sending end of the transmission line. Here this is the receiving end of the transmission line. The transmission line series parameters, you can see that they are having resistance and inductance that are uniformly distributed throughout the line. And there are shunt parameters, shunt conductance and shunt capacitance between the lines or between the line and the ground. Okay, so here, though these parameters are distributed throughout the conductor, for our analysis, we will assume that they are lumped at one place. So the circuit analysis will become easy. Okay, so here there are four parameters that are uniformly distributed throughout the line. Next, we see how to calculate the resistance of a solid conductor. Though the contribution of the line resistance to the series line impedance can be neglected in the most of the cases, but is the main source of the power loss. What is the formula for copper loss? We know the copper loss, the average copper loss in the conductor is equal to I square into R, where I is the RMS value of current flowing through the conductor and R is the resistance of the conductor. Okay, so while considering the transmission line economy, the presence of resistance must also be considered. So we have seen the effective AC resistance is given by the formula RAC is equal to P average by I square R, where I is the RMS value of current, P is the average copper loss, RAC is the average is the AC resistance. So this is given by equation 1 where the power is expressed in watts and I is expressed in amperes. Next, DC resistance. Ohmic or DC resistance is given by the formula R is equal to rho L by A, where rho is called the specific resistance or resistivity. L is the effective length of the conductor and A is the cross-sectional area of the conductor. Now, the effective resistance that is given by AC in the equation 1 and in the DC that is equation 2 will be same only if the current distribution across the cross section of the conductor is uniform. Now we have studied the AC resistance and DC resistance. What is the significance of AC resistance and DC resistance? Which one is more? Is AC resistance more or DC resistance more? Why AC resistance is more? Okay, let us see. Now, whenever AC current is flowing through the transmission line, now AC current has frequency. We see that the conductor will not have uniform impedance throughout its cross section. Whenever AC current is flowing through a conductor, the core of the conductor will be experiencing more impedance than the surface of the conductors. Therefore, the current density is not uniformly distributed throughout the cross-section area of the conductor. The impedance of the inner layers of the conductor is more than the impedance of the outer layer, that is the skin of the conductor. So we know that current will flow through the path of lower impedance. So most of the AC current will flow through the skin of the conductor and less current will be flowing through the core of the conductor. That is why the effective resistance in AC is more than the effective resistance in DC. If you want to make the AC resistance and DC resistance equal, the current distribution must be uniform throughout the conductor. So generally, the AC resistance is taken as 1.5 times the DC resistance for calculation purpose. Resistance depends upon these following factors. It depends upon the resistivity of the material, that is, resistance is directly proportional to the resistivity. It depends upon the length of the transmission line. More length means more resistance. It depends upon conductor size. It is inversely proportional to the area of conductor. If the cross-section area is more, that means the resistance is less. That means thin wires will have more resistance, thick wires will have less resistance for a given length and a material. Current magnitude. So we know R is inversely proportional to current square. So if current is increasing, the resistance will also decrease. Frequency. So as said in the skin effect, due to the frequency, that is AC current, will flow through the conductor and the resistance will be altered. Spiraling of conductors will change the effective length of the conductors and thereby it affects the resistance. Resistance depends upon the temperature given by Kelvin's law. The resistance depends on conductor coefficient of temperature. Okay, so that is depend upon the material. We will discuss in the next slide. Variation of resistance with temperature. For small changes in the temperature, the resistance of the conductor increases according to this equation. So R2 is equal to R1 into 1 plus alpha into T2 minus T1, where T2 is the temperature for the resistance R2, or you can call it as R2 is the resistance at a temperature T2. Similarly, R1 is the resistance at a temperature T1 and 1 plus alpha. Alpha is called temperature coefficient of conductor in per degree Celsius. So if alpha is positive, the resistance increases as the temperature increases. If alpha is negative, the resistance is inversely proportional to temperature. The value of alpha depends upon the type of material. For most of the metals, alpha is always positive. For semiconductors, you can consider alpha as negative. So equation 3, it is used to determine the temperature. It is used to determine the resistance at any given temperature. Suppose you take RT2 is the resistance at temperature T2, RT1 at a temperature T1. So here, this is the relation between these two resistors if they are having the same material and same temperature coefficient. So this is equation number 4. Now based on these four equations, based on these four equations that you have studied, let us do some problems. So this is the problem. Carefully read the problem. There is a transmission line whose length is 3 kilometers. It is having 19 strands of identical copper conductors. All the strands area is identical. Each is having a diameter of 1.5 mm. Because of the twists of the strands, the actual length of each conductor is increased by 5%. You have to determine what is the resistance of the cable if the resistivity of the copper is so and so at a given temperature. So read this problem carefully and determine this answer. You should get the resistance of this cable. So here you see this is the given length of the cable, 3 kilometers, 1 kilometer is 1000, so 3 kilometers 3000. The number of strands is 19. Diameter of each strand is 1.5 mm. So these are the strands you can see here. So each strand, there are 19 strands. Each strand is identical, having same cross section, that is same diameter. So 1.5 mm each. So what is the diameter? 1.5 into 10 power minus 3 meters. We are converting all the quantities into SI quantities. They have given that the actual length is increased by 5%. So the length of conductor is 3000 meters plus 5% is increased. So we are adding 5% of 3000, that is 3000 plus 5 by 100 into 3000. So which is nothing but 3150 meters. The resistivity of the copper is given as rho is equal to 1.7 micro ohm centimeter. Micro means 10 power minus 6 and centi means 10 power minus 2. So converting them into SI units, we get 1.72 into 10 power minus 8 ohm meter. Now let us see the calculation. First of all, we find out what is the area of cross section of entire conductor. It is equal to total number of strands into area of each strand. So area of each strand is given by formula pi r square or pi by 4 d square. 19 strands are there, so 19 into pi by 4. Substitute the value of d here. So 1.5 into 10 power minus 3 whole square. So you get as 3.3575 into 10 power minus 5 meter square. This is the effective cross sectional area. The resistance of conductor is given by R is equal to rho L by A ohms. So rho, you substitute the value of rho here. This one you substitute here. You substitute the value of L. You substitute the value of A. So finally you will get the resistance as 1.6136 ohms. Clear? Similarly, we will see another problem. Here, a sample of copper wire has a resistance of 50 ohms and the temperature coefficient of resistance is 0.04004009 per degree Celsius at 10 degree Celsius. So here the temperature T2 is given, T1 is given with respect to the resistance 50 ohms. The temperature coefficient is assumed positive. We have to find out what is the temperature if the wire resistance is increased by 10%. So if you solve this, you will get the answer 35.44 degrees Celsius. So let us see the answer. So given data, R1 is given as 50 ohms, alpha is 0.00409 per degree Celsius, T1 is given as 10 degrees Celsius. We know the formula R2 is equal to 1 plus, it is increased by 10%. So 1 plus 10% of R1, that is 1.1 into 50, that is 55 ohms. R2 is 55 ohms. You have to find what is T2. We know the formula R2 is equal to R1 into 1 plus alpha into T2 minus T1. So 55, 50, you substitute the values, whatever values you have, you will get here 50 by 50 is 1.1. You bring this to the left hand side. Okay, fine. Thank you. So that's all for today's lecture. So to summarize, we have studied what is the resistance, how to calculate the resistance, how resistance will vary with temperature. We have resolved two problems to understand what are the factors that which the resistance will vary. Okay. The effective resistance is given by effective AC resistance is given by RS is equal to P average by I square. DC resistance is given by rho L by A. Factors affecting the transmission line. So these are some questions. You have to define resistance. What are the factors affecting resistance? Why is the spiraling of conductors done? How temperature affects the